Hello, welcome to my talk on Cuckoo Index. My name is Andreas, and this is a joint project with Damien, Alex, Peter, and Dave. The majority of this work has been done at Google Zurich. I will first provide some background about the problem we are trying to solve. Then I will give an overview over Cuckoo Index and dive into a few design choices. And finally, I will present some experimental results. In modern data warehousing, data skipping is essential for high query performance. For example, Google's internal Power Drill engine skips more than 90% of data on average during query execution. The enabler of this high amount of data skipping are secondary indices, such as min-max values or Bloom filters. These filters are typically stored per column and chunk of data, or stripe, as we call it here. So for example, when querying for the country CH, we probe all Bloom filters. If a filter returns false, we know we can skip that stripe. Otherwise, we need to load and scan the stripe. Cuckoo Index addresses three issues with Bloom filters in this scenario. First, one needs to probe multiple filters, which can be expensive. Second, a unique value, such as CH, might occur in multiple stripes and is hence stored redundantly in multiple filters. And third, filter lookups can be false positive, causing unnecessary I/O. On a high level, Cuckoo Index combines Cuckoo filters with bitmap indexing. A Cuckoo filter is essentially a Cuckoo hash table, with the difference being that keys are represented by a short hash value, also called a fingerprint. Also, keys in a Cuckoo filter do not have an associated value. Now, in Cuckoo Index, each fingerprint stored in the filter is associated with a value. Specifically, each fingerprint maps to a bitmap indicating qualifying stripes. So for example, when querying for CH here, we first check its primary bucket and find that A0 doesn't match the stored fingerprint BE. We then check its secondary bucket and find a matching fingerprint. So we retrieve the corresponding bitmap, which determines that we only need to scan stripe 0 in this case. Note that Cuckoo Index produces 100% correct mappings for positive lookups. This is in contrast to per stripe Bloom filters, which can produce false positives. In the following, I want to give you an idea of the challenges that come with this design and how we solve them. To ensure 100% correct lookups, we need to resolve fingerprint collisions during inserts. We considered three different options. First, one could union the associated bitmaps, which won't consume any extra space, but will introduce false positives. Second, one could store colliding entries in an additional full-fledged hash table. This design will ensure correct lookups. Or third, we could use variable-sized fingerprints. So instead of, for example, using 8 bits per fingerprint, we use as many bits as needed to break the tie between colliding entries. We opted for this design as it is both space efficient and ensures correct lookups. Now, an interesting insight is that we not only need to break the tie between fingerprints in a certain bucket, but we also need to consider fingerprints that are stored in their secondary bucket and have that bucket as primary. The reason is that we would encounter a collision when probing a key's primary bucket, even though it is stored in its secondary bucket. That means keys stored in their secondary buckets may influence the fingerprint length of the primary bucket. To mitigate that effect, we want to maximize the number of keys stored in primary buckets, as those don't affect other buckets. To maximize the primary ratio, we considered three alternatives. As a baseline, we used the classical Cuckoo kicking algorithm. We also implemented a variant based on maximum weight matching on the Cuckoo graph, which finds the optimal solution. And we devised the heuristic that prefers kicking items that reside in their secondary bucket. We found that our heuristic achieves primary ratios within 1% of the optimum, while being 100x more efficient than our test data. A nice side effect of this optimization is that keys are now found sooner during lookups. While positive lookups are mapped correctly, negative queries can obviously lead to false positives. So after placing all fingerprints and making them collision-free, we may allocate additional bits to certain fingerprints to control the overall false positive rate. The intuition here is that certain hash collisions are worse than others. For example, a collision with US in this example, which is associated with a dense bitmap, is worse than a collision with CH, which maps to a sparse bitmap. We hence devised the heuristic that considers both the probability of a hash collision and the density of the associated bitmap to control the overall false positive rate of the filter. Note that the paper also contains a description of our dense storage layout for variable length fingerprints and of our new unaligned bitmap compression scheme that is more space efficient than roaring while still allowing for random access. Finally, let's look at a few numbers. Here are some results on IMDb and DMV data with 65,000 rows per stripe and a 1% false positive rate. On IMDb, we found Cuckoo index to be 1.4x to 6.4x smaller than Bloom filters. The only exception being the high cardinality column title, for which Cuckoo index requires 10% more space. However, we argue that Cuckoo index is still favorable over Bloom filters in this case, since it does not produce any false positives for lookups with keys that occur in the data. On DMV, Cuckoo index is consistently smaller than Bloom filters, with space savings of up to more than 10x. In this experiment, we vary the hit rate of lookups and show the false positive rate on the y-axis. While Bloom and XOR, a Bloom filter alternative, are largely unaffected by the hit rate, Cuckoo index strongly benefits from an increasing hit rate, since it guarantees exact results for positive lookups. With that, I conclude my talk. Thank you.